Hello everyone, it's Alex here, and today we're going to analyze the data we extracted in my last video. If you did not see that video, the link will be in the description down below, but you don't necessarily need it in order to follow along today. So, we have already extracted the temperatures and vapor pressures of water from this table in the Dortmund databank. We're going to use these temperatures and pressures to estimate values for the Antoine equation, as seen here. Antoine equation relates the temperature and vapor pressure of any pure substance using three experimentally calculated constraints, A, B, and C. We're going to guess and check A, B, and C in order to calculate their values. But before we do any of that, we need to load up some more libraries. This first one is Jack's NumPy. Jack's NumPy is similar to NumPy that we have already imported, but it has a couple more tools that can help analyze our data. The next thing that we're going to want to import is from SciPy, and it's an optimize function. It's called minimize. Minimize will be helpful for when we guess our values for A, B, and C, and we calculate our vapor pressure. We can then compare it to the vapor pressure that was in the Dortmund databank table and see our error. And then minimize will help us minimize that error. The next one is going to help us plot this data. We're going to be able to make subplots of our data so that we can more clearly see it. Now that we got our libraries loaded up, we can start analyzing our data. So if you remember, data is an array with all our temperatures and all our pressures in two separate columns. But for the Antoine equation, we need the log base 10 of pressure. So T is going to be the same as our T string, and it's just going to be the first column of our data set. And then log of PV is going to be log base 10 of 1000 times the second column of our data set. Log over there, hit enter, and now we can start plotting this. So the first thing we're going to want to do is we need to make subplots of one row and one column. Just a blank canvas for us to put our information on later. Next, we're going to add a scatter plot of all of our data. X values are going to be our temperatures, and Y values are going to be our log PVs. Now, I'm going to copy and paste a little bit into here. It's all optional things. Markers just shows that we're doing points on the graph. Adjust the marker size, color. Marker line color is the outer border of the markers. Line width, and we named this plot data. We're going to update the layout. It'll automatically give us a certain layout, but this one I find looks better. And then we're going to add titles, temperature in Kelvin for the x-axis, and log base 10 of pressure in pascals for the y-axis. Then we're going to show the figure. And we get something like that. The next thing we have to do is we have to start guessing some A, B, and C values so that we can calculate those out. So in order to do that, we have to define a model. We're going to use A, B, C, and our temperature, which is the other component of the equation. We're going to return the equation itself. If you remember in the Antoine equation, log base 10 of pressure is equal to A minus B over C plus D. So we're going to do A minus B over C plus D. And that will be our equation. Now, first thing we have to do is we have to guess what our values are going to be. So these can be any arbitrary numbers. Now, we want to analyze these numbers, and it will be easier to do that if they're all together. So let's call this string of numbers x naught. In it, we're going to put our A guess, B guess, and C guess. Now that we got all of our data how we want it, we can start writing out the script that will help us reduce our squared error. So we're going to use x, which is our guesses for A, B, and C, our temperature, and our log of vapor pressure. Going to make a model of our vapor pressure that's going to be the same as the model that we defined up here, except this one will be able to change freely without affecting the model that we already established. So it's going to be x naught, which is our A guess, x1, which is our B guess, and x2, which is our C guess, plus temperature. Now, our error is going to be a jack-snumpy script of sum. We're going to find the difference between the model PV and our log of PV. And we're going to square it because we're doing a squared difference. Then we're going to return error. Now we're going to do a square error scaled. The scaled square error is scaling our ABC values slightly and finding the difference of the vapor pressure from the scaled values so we can figure out which way we need to adjust our values to get to the established values of A, B, and C. So this one is quite similar to the previous one, so I'm going to copy and paste that over, except we're going to multiply a couple of our guesses by some numbers so you can see the difference when we scale it. Now we get to return a result. And our result is going to be our minimize function, the squared error. X naught is going to be equal to the x naught that we established earlier. Args are our arguments, which is our T and log base of vapor pressure. Our TOL, which is the tolerance for termination. We're going to set that to 1e minus 10. So we want it to be pretty close. And then Jack, which is a method for computing the change in the derivative of the function. Run that. Small typo up here. And another one right there. And it works. And now we can check our result, and we get x values equal to our a, b, and c for the Antoine equation. Now that we have our a, b, and c, we can plot it out. Linspace is just a way to set up evenly distributed points across a certain interval. So we're going to be doing it from the first point we have on the vapor pressure of water table to the last point. We're going to add a scatter plot again. X is still going to be equal to our t, but it's t model because we're using our modeled Antoine equation. And then y is equal to our model, which is our original set up here, times our result dot x, because we're looking for the x part of this result, and our t model again. We're going to do mode lines this time because we want a singular line going all the way across our graph. Line width, set that to 1, and we're going to name this one Antoine. Fig show. Couple errors, but there we go. Now we've plotted out our Antoine equation. So say you don't know the pressure of water at 600 degrees, you can use this equation to figure it out. And this is great because if you have a pure substance that doesn't have established Antoine constants, all you need to do is calculate or experimentally find 3 of these data values, plug them into here, and you can figure out all the rest of your data values. Hope that helped, and I'll see you again soon.